Hi, it's Miss House, and I would like to give you some highlights from section 3.1. You should also look at the full video lecture that is provided by your textbook that's posted in my math lab. So the first thing I want to talk about is what a limit actually is. So this is the limit of a function f of x. Given a function f of x and a value x equals a, as x gets closer and closer to a from both sides, and the value of the function gets closer and closer to some specific value L, then we say that the limit as x approaches a is L, and that's written LIM for limit, f of x, the name of the function, x with an arrow pointing toward a, whatever that x value is, equals L some number. Now I want to demonstrate that by showing you the graph of a simple polynomial function. And here's our a value here, and we're going to come toward a from the left and from a from the right, and because it goes to the same place called L, that's why we can say the limit as x approaches a of this function f of x is L. Now, it's important to note that even if this point didn't exist here, so let's say there's a complete hole in the graph here, like you sometimes get when you have rational functions, and that function value is defined up here to be something else that we'll call m. Okay? Even though the function value is not the same, it's m, as it is as x approaches a from the left and a from the right, because it's honing in on the same place, this L value, as I come in from the right and as I come in from the left, as I'm going toward this x value, we still can say that the limit as x approaches a of f of x is L. So in other words, the function value doesn't have to be the same as the limit for the limit to exist, but both sides of the function, okay, whether you're using the algebraic rule or looking at a graph, they have to be honing in on this specific value called L. Now, limits do not always exist. For example, if the limit from the left, and that's what this a minus 1 means, it means we're coming in from the left to a, and the limit from the right, we're coming in from the right toward this a value on x, then we say that the limit of f of x at a doesn't exist. In other words, if the limit from the left is not the same as the limit from the right, the limit at x equals a does not exist. I'm going to show you a picture of that. So notice right here what's happening at -4. As I'm coming toward -4, my function is going towards 2. So see how as I come in from the left side, it goes to -4. And then when I'm coming toward -4 from the right side, it's going to 3. So as I go to -4 from the left, it's going to 2. And as I go to -4 from the right, it's going to 3. So it's this gap that's the problem. The limit doesn't exist because there's a gap in the graph. It's not going to the same place. Now here we're okay because look, as you come in from the left, it's going to this point, and you're coming in from the right, it's going to this point, and it's okay that there's no function value there, as long as it's honing in on that specific value. Okay. Now, here are other times when the limit doesn't exist. If f of x approaches infinity or negative infinity as x approaches a from both sides, the limit does not exist. Although we do write the limit as x approaches a of f of x is infinity, or the limit as x approaches a of f of x equals negative infinity. Well, here, that's not the situation. In this particular part right here where this is -6, the limit from the left is different from the limit from the right. It's true, the graph is going to infinity and the graph is going to negative infinity, and the limits are different. Okay, so it's really both the limit from the left and the limit from the right are different, but we can't write the limit is infinity or negative infinity because they're going to two completely different places. Here, however, as we come in toward x equals 3, watch what happens. As I'm going toward x equals 3, this graph is going to negative infinity, and that's from the right. So if I'm coming in toward 3 from the right, the graph's dropping to infinity. As I'm coming in toward 3 from the left, the graph is dropping toward negative infinity too. So we can write that the limit at x equals 3 is negative infinity, but the limit does not exist. Okay, so those are sort of the kinds of situations you will see about limits. Now, there are going to be some limit rules we'll also talk about, but before we talk about those, let's talk about this concept of discontinuity, or the concept of continuity. Now, continuity means that if I trace the graph, I never have to pick up my pencil. When I have to pick up my pencil to go to another part of the graph, that's a point of discontinuity. Look, this where I'm drawing the graph here, and it's going up, and then all of a sudden it's going down, that's a point of discontinuity. Here, if there's a gap, there's a point of discontinuity. Here, if there's a hole, even if the limit exists, there can be a point of discontinuity because I have to pick up my pen to go across that open circle. Here, same thing, I have to pick up my pen to keep tracing the graph. So discontinuity occurs wherever you have to pick up your pencil when you're drawing the graph, or where there is either an asymptote or a hole in the graph, or if the graph is not there at all, we can say it's discontinuous at a certain point. So if there was a complete gap where it didn't even exist, it just skipped over, say it skipped over from 0 to 2, it would be discontinuous from 0 to 2. And the flip side of that is everywhere it's not discontinuous, it's considered continuous. So for example, this graph is continuous between 0 and 3, not including 0 and not including 3, because I can draw my graph without picking up my pencil from 0 to 3, not including those endpoints. All right, so here are some basic rules for limits, and I know these might be kind of small, but here's the summary of what's going on here. If you have a constant function, that is something like f of x equals 6. So there's no variable here, it's only a constant on this side. Well, then the limit is that constant, and here's why. If I draw a quick sketch of f of x equals 6, that's a horizontal line through 6 on the y-axis. Well, if I'm moving anywhere on this line toward a certain x point, I'm always going to be at a y value of 6. So let's say, for example, I pick 2 over here. As I move in toward 2 from the left, I'm still at the level of 6. And if I move in from 2 to the right, I'm at a level of 6. So we would say the limit of f of x at x equals 2 is 6. So the limit of any constant function is a constant. Now, if you have a constant times a limit, the limit of a constant times a function is the constant times the limit of the function. So in other words, you can take this k completely out and just deal with the limit of the function, and then once you get that, you can multiply it times the constant. Now all three of these, 3, 4, and 5, contain similar ideas, that if a function is made up of the addition or subtraction of functions, the multiplication of functions, or the division of functions, you can separate these and take the limit of each part. So if it's added or subtracted, you take the limit of the first part that's added or subtracted to the second part. If they're multiplied, you take the limit of the first one times the limit of the second one. And if it's divided, you take the limit of the top one divided by the limit of the bottom one. But always remember, zero denominator is not allowed. So in addition to this, I'll try to work some problems on video, but you have the video from the textbook, and you have examples worked out in writing also already posted for section 3.1 and 3.2. Now I touched a little bit on continuity as I did this, but there are a few other things from 3.2 that I want to highlight, and I'll do that in a different video.